Swayam Prabha. Digital India. Educated India.
The first problem, which was the temperature of the earth, we already saw the solution to the problem in yesterday's class. So basically the sun is considered to be a black body whose outer surface is at 5800 Kelvin. That is not the actual temperature. The temperature of the sun is millions of Kelvin at its core. The outer surface of the sun has a temperature equal to 5800 Kelvin. That is enough for us. So from there the radiation is coming, it is falling on all the planets. That is why we are able to have sunlight, daylight, this thing, and because of that the earth is having a good temperature at which we can survive and all that. So I told you we had discussions about this in the previous class, in one of the earlier classes. So you have to take the surface temperature to be 5800 or 600 Kelvin, find out the black body emissive power of the sun, that is the outer surface of the sun, sigma Ts to the power of 4, divided by pi, you will get I, intensity, watts per meter square per steradian. Okay, keep it. Now work out the solid angle. Solid angle is always calculated with respect to the receiving area. Okay, so the receiving area is the earth, so it receives, because it is from a sphere to sphere, if you have a plane cutting, so it is only pi r squared or pi d square by 4. So the area which you have to consider is pi d square by 4 for the earth, pi d square by 4 for the sun. Okay, now the receiving area is pi d squared by 4 for the earth, multiplied by the cos theta divided by the distance squared, that will give you the d omega. Now once you have the solid angle, then once you have the intensity, so I d omega cos theta, what else is there, into, so that will give you the, so multiplied by, yeah, so that will give you the q incident. Q incident must be equal to sigma Te to the power of 4 into 4 pi r squared, because the area of emission of the earth will be 4 pi r squared. Once you do that, you are able to get the equivalent temperature. So the earth's temperature came out to be some 279 Kelvin, but there is a technical flaw in what we have done, because the earth is not a black body, it has got a albedo, that is it has got a reflectivity. If you consider that, you will get a temperature which is slightly different from 279. So the second problem most of you have done, but for the sake of completeness, so I will go through this again. This is the hemispherical spectral emissivity. So the first step is to plot it like this, epsilon lambda versus lambda, then evaluate. There are 3, lambda 1, lambda 2, lambda 3. So calculate lambda 1 T, lambda 2 3, lambda 3 T. This T corresponds to the 1200 Kelvin, which is the temperature of the surface. So now from the F function charts, so this is, so from the charts you calculate the F values, and then you have the formula. So epsilon is epsilon 1 into f of 0 to lambda plus epsilon 2 f of lambda 1 to lambda 2, epsilon 3 lambda 2 to lambda 3, and this goes up to infinity. So this is lambda 3 to infinity, which means 1 minus f of lambda 3t. Okay, that f of lambda 3, all that we have found out, this is 1 minus 0.819. If you add all that, you will get emissivity equal to 0.464. Now if you calculate the absorptivity, you have to use the temperature corresponding to the temperature of the sun. Okay, but it is perfect to use epsilon lambda is equal to alpha lambda, because it is I told you it is diffuse surface. I told you it is diffuse surface. So from the Kirchhoff's law, you know that emissivity is equal to absorptivity, that is spectral. Okay, but you should not make the mistake of calculating taking T to be 1200 Kelvin, then you will again calculate epsilon alpha also equal to 0.464, which is not correct. Alpha is basically the absorptivity of the incident radiation. So the incident radiation is coming from somewhere, from where it is coming from the sun. So you have to take the temperature of the sun. Otherwise I should give you information on I lambda I. I will say no, it increases from 0 to 4000 watts per meter square, decreases, increases. Since I have not given the distribution, you have to use the black body function, and then so repeat the same procedure, except that you will use 5800 Kelvin. Now we got the alpha. So 6 marks plus 6 marks, 12 marks. Okay, then we will go through the other portion little more carefully, because a lot of you were blinking yesterday. how we got that lambda greater than lambda half? What is it, optimal resolution, what is it? Yeah. So the part C of the question is, what is the wavelength for which 50% of the total radiation emitted by this surface lies in the spectral region, lambda greater than lambda 0.5, okay. Now can this be shown? Difficult, okay. Now all of you have this f function chart, so when I said lambda, when I asked the question what is the wavelength for which 50% of the radiation is emitted, all of you thought that you must go to the column number, the last column number 5, and find out the black body fraction and find out where it is 0.5. So it is not 0.5 exactly, at 4000 micrometer Kelvin it is 0.48, at 4200 it is 0.516. So you thought that you are very intelligent and you interpolated, and then very intelligently interpolated and got the answer. You said some 4100 something, so therefore lambda into this thing is 4000 something, T is given to be 1200 Kelvin, therefore this is point. That is perfectly okay if you have a black body or if you have a grey body, okay. But the funda now is this fellow is having a funny distribution. So though the f function remains the same as a black body, its contribution varies in the various wavelength bands, because epsilon 1 is not equal to epsilon 2 is not equal to epsilon 3. So you must first understand the futility of an exercise where simply you took 0.5 in the last column and said no this is 50%. Are you getting the point? What that is correct for a black body as well as for a grey body. Not so, the body under consideration is what? Blue body. What is it? It's called a non-grey body, okay. It is non-grey, it is not grey, it is not the color. Non-grey means that fellow is having a distribution, that is epsilon is a function of lambda, okay. Therefore you have to, now I have to make an assumption, I do not know where that 50% lies, okay. I do not know where the 50% lies. So but now my intelligent guess is, since the Wien's displacement law gives me 2898 micrometer Kelvin is the maximum, so part C is not so straightforward, that is the first thing. First thing you have to recognize, it is not so straightforward, it is not simply taking the last column and giving, therefore, so it may involve some tedious iterations. Suppose I make it very painful, 0 lambda less than 1.2 is 0.75, 1.2 to 1.8 is 0.7168, if I do like that you are finished, okay. But now so where can this lambda half lie? What is this lambda half? That is f of 0 to lambda half. No, it is not even this. It is not even this. What does it mean? Where first we have to find out what this lambda half is, okay. Total radiation emitted by the body. Epsilon, correct. What is this? 0.46, 0.46. Yeah, what is this? All this is not required for working out the problem, but we will do it for the sake of completeness. Per meter square. Now Okay. Now what I want is is it right whatever I have written? Deepak, is it okay? Okay. So what happens to this? I am not going to use this. Vikram is RG, so that's not going to be used 27.2. If some people want to be clinically perfect, please keep this 27.2, multiply each of these terms by sigma t to the power of 4 and proceed. It will give the same answer. But the danger there is when you do sigma t to the power of 4, you may make some more mistakes. Okay. Now I am assuming that I expect this fellow to lie between 2 and 4. How can I make such an assumption? Are you getting the point? How many of you are not able to follow my line of argument? I am saying that the buck stops with epsilon 2. That means I am expecting that 50% interval to be between 2 and 4. It is reasonable to assume because the temperature is 1200, means displacement log gives me lambda max t is approximately 3000. 3000 by 1200 is 2.5, correct? So around 2.5 it is peaking. So I expect when it is peaking, I expect that between 2 and 4 I can get this 50%. I may be wrong. If I do not get that, I will go to epsilon 2 or epsilon 3. Are you getting the point? Fine. Now can you do this? So this will be what is the first term? 0.105 plus epsilon 2 is 0.55. What is epsilon lambda 1 lambda 2? Not 0.2, I do not know lambda half, right? 0.607, okay. I can solve for the x, okay. So x turns out to be point, is it 607 minus x, it is correct. It's okay, right? Correct. So x is how much? Yeah, so 0.607 minus x is all right. No, wait. X minus 0.6. Yeah, so algebraic. Okay. So x equal to 0.376. Go to the f function chart. Point out where you get this 0.376. So you have to interpolate between. Yeah, what is the problem? What?
No, the first value
X should be greater than 0.60.
X is?
Point should be greater than 0.60.
Greater than 0.607. Why? No. Just hang on.
607.
No, that is not 0.607 sir.
0.14.
0.14026.
There may be mistake here. Let us. What is f of 0 to lambda 1? Ah. So what should so it will be x minus?
Minus 0.14.
I made so many mistakes. X minus
0.14.
Hey Umesh, now is it okay? Let's check 0.2, 0.2311 divided by, so it should be fine, 3761. Is it correct? Yeah. So if you look at 0.3761, go to the f function chart, take the last column corresponding to 0.3761, you back calculate lambda into t. So what should be the answer? Equal to 3000, what is it? 3468. Okay. Okay. Lambda max is 2.8. 4 I wanted you to write that this lambda half and lambda max are close to each other. Some people have written 2.89 is greater than 2.4, therefore lambda half is greater than lambda max, and but from in the whole spectrum of 0 to infinity, one was 2.89, one was 2.41. I don't know why you are not able to see the similarity, but you want to see only the difference. Okay. Now third question. Yeah, it was a straightforward question. So there was a small typo. This came as 45. Okay, this is supposed to be 60 to 90. So this is a directionally okay. So can this fellow be knocked off? And one integration with respect to phi will give 2 pi in both the numerator and denominator, that can also be removed. Okay. So two pi by, is that correct? You get a 2 pi in both the, I am making a mistake, I am making a mistake, I am making a mistake, I am making a mistake. Ah, there is only one pi in the denominator because it is solid angle, pi steradian. Okay. I am writing this explicitly so that all of you remember that when you are converting this spectral directional, okay, into what is this? Into total quantities, the 2 will be there here, the 2 will be there. Okay, so long as it is azimuthally isotropic. I gave you the surface is isotropic in the phi direction, that is there is no change. Okay, in this direction we can give one more dependence on that, we can say that epsilon is a function of phi also, then we can make things complicated, but that will be basically an academic exercise. It's very few surfaces have both dependence on zenith and azimuthal angles. Okay, so this is like this. Now straightforward, it is pretty straightforward. So epsilon theta sin theta d of sin theta. Okay, there are several ways of doing it. Some people have done sin theta cos theta, sin 2 theta by 2, and then all that. Okay, so now you can substitute. So this is basically so 0.88, the next is 0.44. No plus, now plus it looks like a very innocuous or very simple problem, but many of you just got rid of the 2 and you got a nice answer of 0.305 or 302. The answer is 0.605 or something. Somewhere the 2 was followed. Okay, so pretty straightforward. So this is 1.76 okay. So I have substituted for sin theta 0.6 something 605. Then so this is the hemispherical this is total hemispherical emissivity. Now I asked you the ratio of the normal emissivity. Normal emissivity is cos of 0, that is 1. Okay, so that is the highest, that is 0.88, right. So ratio is epsilon (1.45). Okay, so 5 marks for this one and 1 mark for this. Okay, so many of you have got it right, but basically some of you have missed that factor of 2. Okay. So the last question is a practical problem which involved energy balance, right. So what is the radiation hitting a roof? Okay, it could be an asbestos roof or it could be a concrete roof or whatever. So for example, if you have so there is a convection on the inside, outside there is also a convection on the inside, but outside convection is because of wind, inside it is because of natural convection. In fact, if it is a roof, you do not expect much natural convection on the inside, because if it is heated at the top, if you have a room which is heated at the top, okay, the hot air will stay here, okay, but somehow I have given you 8 so that I wanted to check whether you are able to add 24 watts per meter square Kelvin to 8 watts per meter square per Kelvin, and okay, otherwise this is stably stratified, that is if the hot air remains at the top it is stable, it will not overturn, okay, because hot air is lighter. Okay, so now there is an incident radiation. So what is the G? I or G is 1150. Out of this there is emitted plus reflected. Here you have emitted. Okay. Now if you do the energy balance, so basically Q net equal to 0. If Q net is not equal to 0, then Q net will be equal to mCp dt by d time of the plate. then the dt by deta will be non-zero, it will increase or decrease depending on the complex interplay between the various factors. That is not the subject of this problem. You model something where dt t increases and decreases with t time, that is the immersion heater, you have already done that. This is not the goal here, the goal is to find a steady state temperature, okay. So the governing equation will not be a differential equation, it will be a simple nonlinear algebraic equation, okay. So basically 2 epsilon sigma plus did I give 300 or 303? I will just put it as T infinity first equal to 0, right. The net emitted plus whatever is reflected minus whatever is incident plus whatever is convected must be equal to 0. If everything is going, where is the source? The source is this minus 1150. Rather 0.4 into 1150 minus 1150, which is nothing but, any problem? I give huh? Oh. My notes I had 2 epsilon and all that, then when I was typing I changed, you do not believe, so this before setting the paper, okay. So I have 2 epsilon and all that and 1150, then I changed 1150 to 1200, but I got the answer for 1200 also. Okay, this is the way we set papers, okay. Fine. Now this is a nonlinear equation. So Ti plus 1 plus okay. So let us start with Ti equal to 310, so it will drive it, so that will drive it right side, so you will have 303 plus 720 minus whatever. So in 3 or 4 iterations you get after the 3rd or 4th iteration, okay. So if you have got some other answer, 32
will be for the other one.
yeah correct. Now how will you redesign this for a solar collector? Is this clear to everybody? So we are done with the quiz now. So if you have started iterating, I would have given 5 or 6 marks regardless of whether you got the right answer or, and if you have got something close to 323, 324, 325, you would have got 10 marks, okay. Now so what the solar people will try to do is they will try to put some that is okay, that is one thing, non-selective surface, already emissivity is low, okay. They will have something where absorptivity is 0.6, they may increase it further, they will put there will be a glass cover, okay, so that you can reduce the convection, okay. What they will do is, and then probably they make it like this, then they will have okay, copper tubes. Okay, in those copper tubes you will send water and then you will get heated water. So the maximum temperature will be around T will be around 80 degrees. Okay, so if they want more, then probably they will have to do something like this. So they will have what is a concentrator, and then this will go up, this temperature will go up. This is basically called a line focus because it is like this. Okay, if you want to get if you want to improve further, so probably you will have something here. This is the ground, this is the tower. You will have all these fellows like this. You will track all of them. All these fellows will send the radiation up using these motors. During the time of the day, during the season, you will track all this. Dual degree students must have studied this in many courses. This is called the power tower concept. Okay, so you can get very high temperatures here, and you send a fluid here, a thermic fluid, a fluid here, which will get heated up, and that fluid can be used in a secondary heat exchanger where water is converted to steam. You can run a power plant. There is a plant called Solar One in Barstow, California. They are also developing something called Rajasthan Energy Development Agency is trying to build. Okay, but they have been saying this for a long time. So it takes a lot of area, and there are lots of issues, maintenance issues, and all those things. And then because you have all these motors, right, for tracking all this, and so they frequently give rise to problem. This is one set of people who are working on this. There is other set of people, electrical engineers and physicists, who are directly working on thin films, and they will directly do the solar photovoltaic conversion. Because this is again thermodynamics, then second law, and then we cannot produce more. It is impossible to construct a device which is operating in a cycle. All those laws will be applicable. So you can directly use a photovoltaic, but the costs are very high. So here there are other reasons. There are other problems like initial investment is high, and okay, maintenance issues and so on. Okay, but they can supplement. You can't have. It's very difficult to get a 3000 megawatt or a 4000 megawatt plant with all this. Humongous areas required. But a single for the Ramagundam super thermal power plant, you got 5 into 500 megawatts, 2500 megawatts. In 3 kilometer by 3 kilometer whole plant, township, everything, you are able to generate thousands of megawatts. Okay. So coal is also solar energy only. Everything is solar energy. Correct? Wind is also solar energy. Correct? It is not really renewable because the sun is not an inexhaustible source of power. But anyway, when you say it's renewable, it is basically you are looking at the scales, time scale. For our lives, for our time scale, it is renewable. Okay, in a cosmological time scale, it is not so. Okay. Now we will get rid of this, and then we will get back to our transmissivity. Okay, that is the last property which we have to study. I will define transmissivity, and then tomorrow's class we will work out 2 problems and wind up our discussion on properties. Okay, so now no spelling mistake? Okay. Right. Transmissivity, for example, if you consider glass, what is the story of the radiation falling on this? Did we say I for falling? incoming is I, INC, okay, incident, good. So what is the fate of the radiation which is falling on this? Don't worry about the emission. What can happen to this? Reflected, okay. Then absorbed is it goes inside. Now as far as glass is concerned, it is not opaque, so some will go through. Okay, so for a transparent medium or a semi-transparent medium or a medium which is not opaque, there is a possibility that the radiation will go through, penetrate the medium and come out of it. Therefore, an additional property enters, which is basically the transmissivity. We already saw that okay, this tau it is also a dimensionless property. It can also have a, it also has the limit 0 to 1. It is opaque surface, it is having tau equal to 0. If it has got 100% transmittance, okay, for example glass, some surfaces will have 90% plus in certain portions of the spectrum, then the tau will be equal to 1. And just like our emissivity, absorptivity and reflectivity, this fellow can also misbehave. That means it can vary with respect to lambda, it can vary with respect to theta, so it can lead to complexities. But we are talking about thin media, okay, a thin layer of glass, okay, a lens or a prism or a filter, okay, or the atmosphere. Now suddenly I am saying I am equating a glass to atmosphere. How can I consider atmosphere to be thin? Can I consider the atmosphere to be thin? Again it depends on the relative scale. Compared to the radius of the earth, the diameter of the earth from the problem is, quiz problem is how much? Radius of the earth is 6378 kilometers. The radius of the earth is 6378 kilometers. The atmosphere may be 70 or 80 kilometers. So the height of the atmosphere divided by the diameter radius is so small, therefore the atmosphere can also be considered as thin. What is the advantage? Then I can consider it to be one dimensional. I can consider all the properties to vary only with the height or z. That makes matters very simple. If everything is a function only of z, then I kill the variation of transmissivity with respect to direction. So the concept of a directional transmissivity becomes redundant for a one dimensional medium or a plane parallel medium. Because it is so easy to work with that, we stick to that assumption and say that most of the times you are interested in plane parallel assumption, that does not lead to severe error, okay. So basically plane parallel assumption. Okay, what is this plane parallel assumption? If this is the thickness, this is the L for example, L by thickness is much greater than 1. So properties varies across this height only, therefore directional transmissivity is superfluous or redundant. There is no need to worry about a directional transmissivity. It makes life easy for us. Example, of atmosphere, glass, okay. Examples of media which are not opaque, jet exhaust, right. Okay. Non-opaque what? Media, correct. We can't say surface, huh? Non-opaque media, some examples, atmosphere, lens, filter, this thing. So the concept of a directional transmissivity becomes redundant. So we have to define spectral and total and then be done with it. Okay. So spectral transmissivity. So you want to put tau of I want to use tau lambda should be a function of lambda, and shall we put it as d or L thickness? T. Okay, you want to use T. So it is basically I lambda I incident, the denominator, numerator, yeah, so I lambda fine. Can it be greater than 1? No, it cannot be greater than 1. Fine. Now, so what is this? What is T? Thickness. A medium which absorbs, which can scatter and which can also transmit is called a participating medium. Okay. In a participating medium, the basic difference between a participating medium and the surfaces we considered so far are, the basic difference is, as far as surface is concerned, the reflection, absorption, they were all happening in the first few micrometers. They were all surface phenomena. That is why I said radiative surface properties. But in an atmosphere, the radiation penetrates deep into the atmosphere, it agitates all these molecules. They may absorb this, they may scatter, that is they may reflect, it may transmit. Because of its temperature being greater than 0 Kelvin, it can emit as a volumetrically. This is different from the emission of a surface where it was emitting from the surface. Now this whole gas volume may emit and it may scatter differently in different directions. That is called anisotropic scattering. So the problem gets lot more messier. And the governing equation is called the radiative transfer equation, RT equation, which was first figured out by Subramaniam Chandrasekhar. Okay, he only wrote the equation and solved it when he was just 29 years or something. Okay, so that is the RT equation. What is RTE? Radiative transfer equation, or RTE, okay, or RT equation. So therefore this is called a participating medium because it participates in the radiation volumetrically, the whole gas volume is participating, as opposed to the surface where all the activity was restricted to the surface. It can get absorbed, but the absorption is very quick. I mean the absorption happens in the first few micrometers, right, for the surfaces, right. Now total transmissivity, so can you give an expression for the total transmissivity? Tau lambda divided by, you can put all this I lambda, tau lambda, lambda t, all that, do all that, put the bracket, divided by lambda equal to 0 to infinity I lambda I d lambda, very good. Now fine. Now look at this. Watch carefully, please look at the board. Suppose I say that the incident radiation is coming from the sun. The incident radiation is coming from the sun. I am talking about a non-gray surface. I give you the spectral distribution of rho, I give you the spectral distribution of alpha. and I tell you that the radiation is coming from the sun and keep quiet, can you calculate this? Can you or can you not? Yes. How? You will first say tau equal to 1 minus alpha 1 minus open bracket alpha plus rho from whatever is given data or from the graphical distribution. You will recreate the graphical distribution for tau, and then for I lambda I you will take EB lambda corresponding to the sun's temperature. So you will use the F function chart, you will reproduce or create tau based on this and then calculate the tau. So we will work out such a problem in tomorrow's class. We will also work out a problem about the sun control film, how it works. Okay, I will stop now. Okay, so you can work this out for the special case of irradiation from a black body. You know this. What will happen? 1 second. The special case of irradiation from a black body. Lambda 0 to infinity tau lambda EB lambda divided by sigma t power 4 by pi. Okay, if it is no, if I use IB lambda it is by pi, if I use EB lambda it is this one. Okay.